There is a dividing line in chemistry, and that dividing line is the mole. So when you start your chemistry class, you're probably learning things that you've heard before, and definitely learning things that don't involve math. For example, the atom is made of protons, neutrons, and electrons. And you think to yourself, easy, right? And then one day, your professor or your teacher shatters that when they come in and start talking all about the mole. And they don't mean the animal, they mean some crazy chemistry thing that makes no sense. And from there, if you understand the mole, you tend to do well because everything afterwards depends on the mole. If you don't understand the mole, things tend to get more and more difficult because you don't know the mole, so you don't know all the things that depend on the mole. As a disclaimer, this graph is not like statistics, it's just from my personal experience. So if you know the mole, you know chemistry. Hopefully in this video I can break down to you what exactly a mole is and how we use it in calculations. So let's start with an example that doesn't have anything to do with chemistry. Or does it? So this example is about party planning. Let's say that you are hosting a graduation party. Fast forward, you got your diploma, no more chemistry class for you, and you are inviting 100 guests over to admire your diploma. And you have to set place settings for all of them, and you have the requirements that are here. Well, now what if I ask you, how many pounds of plates do you need for these 100 guests total? Well, if I got this question from somebody, I would look at them and think they were crazy, because why would you measure in pounds when you could count 1 plate, 2 plates, 3 plates? The weight is not a convenient way for us to count things, because if I try to make equal weights of plates and glasses, that's not going to make any sense because a plate might weigh different than a glass. So then you won't get the numbers of them that you're supposed to get. We would rather count 1 plate, 2 plate, 3 plates, or even better, 100 plates, 200 plates, 300 plates, and then you wouldn't have to count as many times because you're counting in bigger groups of numbers. So in chemistry, this is applied too, but it's a little bit different. For example, if we're looking at lithium plus iodine makes lithium iodide, and you don't have to know like how ionic compounds work to understand this example. Basically, if I weigh out a gram of lithium and I weigh out a gram of iodine, or even if I weigh out 2 grams of lithium and 1 gram of iodine, that's not going to react exactly in the way that it's supposed to react, or in the amount it's supposed to react, because lithium is a lot littler than iodine. If you look at the periodic table, lithium has less protons, which means it also has less electrons. So we're not going to have the right ratio or the right amount of lithium to iodine. So we need a way to convert mass into numbers, because in chemistry, the difference from our chemistry example and our party planning example is in chemistry, we cannot count 1 lithium, 2 lithium, 3 lithiums, or even 100 lithium, 200 lithiums, 300 lithiums, because those quantities are so little, there's no way we could see or manipulate things that small. We need to talk in bigger numbers. So it turns out that if we're weighing on the scale of grams, then the scale of the number of atom could be like something times 10 to the 24th or 25th power, which is really big. That's also really annoying to put in our calculator all the time, and really annoying to say. Like, imagine if every time you were counting up your plates here, you had to say, oh, well, I'm going to go out to wherever you get plates and buy 3.7 times 10 to the 25th power plates. That would be very annoying. So we don't like to talk in numbers of atoms most of the time. Most of the time, we like to talk in bigger numbers, or not bigger numbers, but numbers that contain lots of atoms in that one amount. So when I'm introducing a mole here, think of it kind of like a dozen, but it's for chemistry. So a mole is Avogadro's number of anything. Avogadro was this guy, and he put a hunk of carbon that was 12 grams on a scale, and he said, however many atoms are in that is a mole. And it turns out that this number is 6.02 times 10 to the 23rd power. And a mole, like a dozen, can be an amount of anything. We can have a mole of atoms, which is 6.02 times 10 to the 23rd atoms. We can have a mole of molecules, which is 6.02 times 10 to the 23rd molecules. We can have a mole of puppies, which is 6.02 times 10 to the 23rd power of puppies, and like freaking suffocate the earth. But Avogadro's number is our way of saying instead of saying 6.02 times 10 to the 23rd, we would say we have 1 mole of whatever it is. Or if I happen to have like 12.04 times 10 to the 23rd, which is not good scientific notation, but hopefully you get the point, that would be 2 moles. And then you can have decimal quantities of a mole because we're not talking about atoms, we're talking about a big group of atoms. So 1.5 moles would not mean we're splitting an atom. It just means we're splitting in half the gigantic number of atoms. And when we talk in moles instead of in atoms or molecules or ions or formula units or what have you, then it's a lot easier because we do not have to deal with these crazy exponents. Instead, our quantities are a lot more manageable. But it's better than mass because it's a system where 1 mole of lithiums would be the same as 1 mole of iodines. So when you get to chemical equations, if I have 2 lithium atoms, forget moles for a minute, if I have 2 lithium atoms, I can react them with 1 iodine molecule and get 2 lithium iodide formula units. Now, the same thing goes for the mole because we're multiplying it all by the same number. So for example, if we had 200 lithium ions and 200 iodine or 100 iodine atoms, then that would still be the same ratio because we just multiplied by 100. With the mole, it's the same concept. I can have 2 moles of this and I can have 1 mole of that, and those quantities will react with each other the same way that 2 atoms react with 1 atom because we're just multiplying everything by the same number. We're allowed to do that in equations, right? If we multiply everything by the same number, it's still the same equation. We do it all the time in math. So then we would get 2 moles of this. And you won't have to see equations for a little bit yet if you're just learning the mole. But let's focus on Avogadro's number. So when we're looking at this number, when we use it in math, the unit we use is per mole, basically. So we put mole on the bottom of the fraction for our unit, and we can put anything we like on the top. So I can say atoms per mole. And remember that when we have something per something, the bottom thing, the per thing, there's 1 of those. Like miles per hour is the miles for every 1 hour, right? So then atoms per mole is saying that there are 6.02 times 10 to the 23rd power atoms in a mole. And as I say this exponent again and again, hopefully it makes sense to you why we have a system to avoid saying it. So we don't have to say atoms. We can say molecules. So we could have this say molecules per mole. We could have this say ions per mole or formula units per mole. And like technically we could say like water balloons per mole or cookies per mole, but like we're never going to do that in chemistry. That's just me making a point, and probably your teacher made the same point with you, that a mole of is just a quantity. So a mole of anything is 6.02 times 10 to the 23rd power number of anything. Sometimes you will see it without a unit. So for example, if your problem includes this, or if they give you this number on your test, it's going to be mole to the negative first power. And remember that anything to the negative first power means 1 over that thing. So you can rewrite this as just the fraction bar over top of it. And that's going to be Avogadro's number. And it varies by class whether you're given this or whether you have to memorize it. But trust me, by the end of your class, if you do everything you're supposed to do, then you will have memorized it just by accident because you use it so many times. Now let's take what we've learned and try an example problem. So we have here a pure silver ring contains 2.80 times 10 to the 22nd silver atoms. How many moles of silver atoms does it contain? So we have our number in the problem, and then we also have 6.02 times 10 to the 23rd power atoms per mole. And that's Avogadro's number, and because there's 6.02 times 10 to the 23rd anything in a mole, then I can make that anything atoms for the purposes of this problem, because then we can take atoms and cancel them out, and we want our answer in units of moles because it asks how many moles. So in order to do this, we want mole to end up on the top of the fraction, and we want atoms to cancel out. If I take Avogadro's number and we divide it by 2.80 times 10 to the 23rd power at 22nd power atoms, atoms will cancel out, sure, but moles will be on the bottom because the bottom of the top of the fraction is the bottom. So we don't want that. But what we can do is try multiplying instead of dividing. What would that do? Well, we can multiply them together, but then moles would still be on the bottom of the fraction. And on top of that, we wouldn't cancel out atoms. We would end up with a unit of atoms squared per mole. Why? Because we have atoms and atoms that are multiplying on the top of the fraction together. Remember, when you have a number that's not in a fraction, it is automatically on the top of a fraction with nothing, or like with 1 underneath it. Now let's try basically the only thing left, which is dividing the other way around. So if we divide the other way, what did I just do? If we divide the other way around, then we have atoms and atoms cancel out, and mole does something interesting because it's on the bottom of this fraction, which puts it at the top. So if we do this, it turns out that we get this answer here. And why this one and not the top one? Well, whenever I teach chemistry, I tend to have problems where students put things in their calculator in the way that you would put them on paper. And calculators are stubborn things, they don't like that, and we have to do order of operations on calculators more strictly, because what happens is that it reads this top one and it says, you are saying 2.80 times 10 to the 22nd divided by 6.02 times 10 to the 23rd. And that's why it multiplies together these two exponents, and you get this crazy looking thing that says times 10 to the 44th power. I bring this up because if you do this on a test, you have a way to check yourself. Because if you look at 10 to the 44th power and ask yourself, does it make sense? It doesn't. Why do we use moles? Remind me. It's because we don't want to talk in these crazy exponents. So if you are looking for moles and you get a crazy exponent, it's probably not the right answer. So if you do the bottom one, which includes parentheses, which basically says this is the whole top of the fraction, this is the whole bottom, and the calculator is more sensitive to bottom of the fraction than it is to top of the fraction, then you will get an answer that looks like this. And that makes sense because it's a reasonable number and you don't have a big exponent along with it, which is the whole reason why we use a mole. So that's how to solve this type of problem. Now I want to introduce a concept called molar mass. So if we go back up to our example with our plates and our party planning and my bad drawings, you might remember I asked you how many pounds of plates would you need for 100 guests? And you would say, like I would say, I don't know, how much do these plates weigh? Well, if we knew that every plate weighed, for example, 2 pounds, if we need 300 plates, it would all weigh 600 pounds. I know that number doesn't make sense. I was trying to make easy math. But if you go to the periodic table, it turns out that they do the same thing for all the atoms. They have numbers that tell us how many grams of this atom are in 1 mole, or 6.02 times 10 to the 23rd atoms of this element. So for example, if we look at sodium, there are 2 numbers in this square. There is a whole number, and there is what is usually a decimal. There are exceptions. So for example, this one looks like it's a whole number. But the whole number that I'm talking about, the atomic number, which in sodium's case is 11, that one will always be a whole number for every element. And the reason why is that's the number of protons. And you can't have half a proton. So this is the atomic number. That is not the atomic mass. This is the atomic mass. It is a decimal because it's an average. It's a weighted average of the different isotopes of an element that are out there. And this number, that is in units of grams per mole. So in the case of sodium, 22.990 grams of sodium is 1 mole of sodium is 6.02 times 10 to the 23rd atoms of sodium. And you might be looking at this number and thinking, wait a minute, my teacher told me that these numbers are in atomic mass units. Well, they are. And conveniently for us, atomic mass unit and grams per mole can correlate to the same number. It's kind of like a milliliter and a cubic centimeter are the same thing, but one is in measurement of volume, one is in measurement of cubic length or distance, but those two things are the same. So you can use either unit, and the problem that you're working on will tell you what unit. If you're talking about one atom of the substance, you're probably using AMU. If you're converting between grams and moles, that's when you use the molar mass. Sometimes people will use the molar mass in a problem when they're not supposed to, and the way that I check myself in those situations is I ask myself, okay, it's molar mass, it has mass, and it has moles. Am I working with mass and moles? Do I want to convert between mass and moles? Because that's usually what it does, is convert between mass and moles. One of these, gram or mole, will cancel out, and the other one, also gram or mole, will prevail. So let's see this in action. This problem says calculate the amount of copper in moles in a 35.8 pure copper sheet, 35.8 gram pure copper sheet. So we have grams and we want moles. So whatever we multiply or divide this number with, we want it to have moles in the unit, so we can have our answer be in units of moles. We also want grams in the unit because we want to cancel out grams. So what number would that be? It's the molar mass, because the molar mass has moles and mass in the unit. So we're going to go to the periodic table, and we're going to find the molar mass of copper, which is a transition metal. It's here, it's Cu. Which one is the molar mass? Is it 29 or is it 63.546? It is 63.546 because 29 is the atomic number, it's the number of protons. We can't have 63.546 protons because we can't have 0.546 of a proton. So I'm going to write this down, 63.546, and the unit is grams per mole. And we can take this number and bring it over to our problem. So now we have two numbers. And notice that you don't get the number in the problem, you have to go searching for it in the periodic table. How can we multiply or divide these two numbers to get moles on the top and grams to disappear? Well, right now moles are on the bottom here in this grams per mole, so we're going to have to divide it to reverse the fraction. So we can take 35.8 grams and divide it by this number. Now another way to look at this is when you divide something, you multiply by the reciprocal. So what we're actually saying here is multiplying by 1 mole over 63.546 grams. And how did I know to attach the number to grams and not to moles? Well, whenever you have a number and a compound unit, or like a unit that has lots of units inside it, like grams per mole, then the bottom always gets an invisible 1, and the top gets the number. So it's this, and then here you have an imaginary 1 with the mole. So now grams cancel out, and we can get an answer. So here is the calculator answer for this one. It's the top. And we can do another problem. Hopefully my calculator image didn't give it away too much. Calculate the mass in grams of a 0.473 mole sample of titanium. This is the reverse of what we did before, but it starts the same. We have moles, we want grams, so we need a unit that has both so we can cancel out the right stuff. Where do we find it? The periodic table of the elements, and we're going to look for titanium 47.867 because 22 is the atomic number, not the atomic mass. So we can bring this over, and the unit on this number is grams per mole, so we can put that there too. And I'm going to already make this grams per 1 mole. So Do we multiply? Do we divide? What do we do? Well, we want to cancel out moles and we want grams to be on the top. Since grams should be on the top of the fraction in the end, we do not want to mess with it. We do not want to flip this. We don't want to divide and multiply by the reciprocal. So we are going to multiply. And if we multiply, this is on the top of the fraction, and this is on the bottom of the fraction, and the units cancel out. I always try to tell students, if you're not sure what to do, if you're not sure which way to multiply or which way to divide, just try something. Try any possibility. And if you know how to do unit conversions, and if you know the proper way to cancel out and to multiply and divide units, then you'll get an answer. If it's right, good for you. If it's wrong, you go back and do it the other way around. And if you do it enough times, eventually you'll remember the right way for each type of problem. So I wouldn't suggest making a table and memorizing, when you go from moles to grams, multiply the molar mass and the amount of moles. That's not going to be as effective as using logic and unit conversions and solving many of these problems until it becomes natural for you. So we can take these two things, Avogadro's number and the molar mass, and we can use them to do conversions. And this image I know probably looks overwhelming. I want you to focus on the middle part of it, because this is probably the only thing you've learned so far. All this PV equals nRT and the molarity stuff, you'll get there. But what I want you to realize is that all of this, even the stuff that we don't know yet, depends on moles. Moles is like the hub in the center, and for a lot of things you have to convert either into or out of it. But for the grams, moles, and particles, which is going to be my kind of umbrella term for atoms, molecules, ions, formula, units, etc., we are going to have to use the molar mass, and we're going to have to use Avogadro's number. And for these two-step problems where you go from grams to particles or particles to grams, you're going to have to go through the mole to get there. So let's try a problem. How many carbon atoms are there in a 1.3 carat diamond? Diamonds are a form of pure carbon. 1 carat equals 0.2 grams. Okay, wait a minute. We talked about grams and moles, and we talked about moles and particles. We didn't talk about carats. Luckily, they give us all the information that we need in this problem. So before we do anything else, let's convert out of carats and into grams so that we can be in a unit that we're familiar with. So we can take 1.3 carat and we can multiply by the conversion factor 0.2 grams per carat. And I did it this way, and I didn't flip it because now we have our carat and carat cancel out and we get grams on the top. So now we are working with a number that is grams. So what can we do now that we have grams? Well, maybe we should get an answer first. 1.3 times 0.2 is 0.26 grams. So what do we do with 0.26 grams? Well, in order to get into atoms from grams, we need to go through the mole. So in order to go through the mole, we have to go grams to moles. What number can we use to go from mass to moles? The molar mass. So for carbon, it is 12. So we can go to the periodic table and we can see that it is 12.011. So we can put here 12.011 grams per mole. And I'm going to put per 1 mole on the bottom. So do we want to multiply this? Do we want to divide it? What do we want to do? Well, if we multiply this and that, then we're going to get grams and grams multiplying together, not canceling out. We're also going to get moles on the bottom of the fraction, not on the top. But if we flip this fraction around, it starts to work. Because we're going to have times 1 mole, I'm going to start a new line, and we can just flip this around. So just take the bottom, put it on the top, take the top, put it on the bottom, and we're going to multiply. And the grams cancel out, top and bottom, and the mole is on the top. So we can do this, and if we divide 0.26 over 12.011, we're going to get 0.0216 moles. And I'm not worried about significant figures because I have a calculator thing here that does it all in one step. But we have that, and then we can take this 0.0216 moles, and we can multiply by what, or divide by what, to get into atoms. We need to use Avogadro's number. Anytime you're actually counting the number of particles, number of atoms, number of molecules, number of formula units, number of ions, we are going to use Avogadro's number. So 6.02 times 10 to the 23rd atoms per mole, or per 1 mole. And the moles cancel out. And if you had done it the other way instead, you would have gotten mole squared over atom if you had flipped this fraction around. So that's how we knew to do it this way. And then you would get a number for this. And what I do when I put it in my calculator all at once, and this helps with like significant figures and making the problem easier, is we basically had, if I'm going to summarize what everything we just did, we had 1.3 carats times 0.2 grams per carat times 1 mole over 12.011 grams. And then I meant to move this. We're going to move this times 6.02 times 10 to the 23rd atoms per 1 mole. And we cross out the units, So you can also do it this way, like all at once, instead of step by step, like I put before. But in this way, what I like to do when I use my calculator is count up all the tops. And I'm not counting the ones, because if you multiply or divide by 1, that doesn't do anything. And all the bottoms, which is just that. And then what you do is you make a big division thing in your calculator where all the tops go in the same parentheses. And for the top, it isn't important to put parentheses, but I like to do it to get myself in the habit. And then in the bottom, if I had more than one number, I would put parentheses to multiply them. And you can even put parentheses without. Like, it's never going to mess you up to put parentheses when you don't need them, but it will mess you up to not put them when you do need them. So you end up getting this number, 1.30433, etc., times 10 to the 22nd power. Now, does this number make sense? Yes, it does, because we're talking about numbers of atoms. So we expect this number to be ginormous, because we are talking about little tiny carbon atoms and how many there are in an amount that we can see. So that's how to do a compound problem, and we can do one more compound problem, like multi-step problem. So calculate the mass of 2.25 times 10 to the 22nd power tungsten atoms. So now we are going the other way. We're going from atoms to grams, because mass is going to be grams. If we look back at our figure, and hopefully we get to the point where we don't have to look at it, but I hope also that this is a nice like starting point. You can take a screenshot if you want. And if we look at this, we want to go this way. We have to go through the mole. So that's going to be our first step, is to take atoms, because this is calculate the mass. So grams is our endpoint. Our starting thing is atoms. So we start with 2.25 times 10 to the 22nd tungsten atoms. And it doesn't matter what kind of atom we have when we're doing this first step, whether it's tungsten or carbon or lithium, because a mole of each one of those is the same number of atoms. So we have this, and then we're going to multiply it by a fraction. And one of these sides, the top or the bottom, is going to be 6.02 times 10 to the 23rd atoms. And one of those sides is going to be 1 mole. Now, do I want to do it like this, with the atoms on the top and the mole on the bottom? I do not, because then the mole will end up in the wrong place and the atoms will not cancel out. So I actually want to do it like this. and like that. And extend this fraction line. But now we have moles because atoms cancel out with atoms. What do we do from here to get mass, aka grams? What number has mass and moles in it? Molar mass. And we can use that to cancel out and convert between the two. So if we go to our periodic table, we can find tungsten. It is W, and it's 183.84 grams per mole, because this other number, 74, is the atomic number, the number of protons. So 183.84, we can put this down here, 183.84, and is this attached to the gram or the mole? It's attached to the gram. So all of these molar masses are called molar masses because they are the mass of 1 mole of that element. So this is that many grams per 1 mole. Do I want to keep it like this or do I want to flip it? I want to keep it like this, because if we do keep it like this, then mole and mole will cancel out and gram will end up on the top where we want it. So now what we can do is what we did before. So we count up all of our bottoms and we can count up all of our tops, and we can put it in the calculator. And here, even though it's 6.02 times 10 to the 23rd and it looks almost like one number, it's 2 because there's a multiplication symbol in the middle and we have to be careful. So here's the calculation for that. And I don't know why there are parentheses here. They should be not there, but around the whole thing. And again, doesn't matter for the top, but for the bottom, we have here 10 to the 23rd going off the screen. And these guys, these are the important ones, or else we would get an answer that does not make sense. So, does this answer make sense? Yes, because we're in mass and we do not want a big exponent. It makes sense. So I hope that this video clarified the mole for you, and I hope it's no longer confusing.